So, today's lecture is about basic segmentation and working with discrete binary structures. We'll start a little bit about also the image acquisition details, how we work with it, and in principle, what people are doing in the beginning is always doing some qualitative approach. I'm going to talk about that. Then basic thresholding, how to use it on different types of images. The question about how to select a good threshold is kind of a lingering question in this lecture. More will come next week, and then a little bit about how to implement it and morphological operations, which are good to clean up. So the applications are usually we have some kind of two or multi-phase material, could be bone and cells, etc. And you want to identify different regions within them. And then you want maybe to fill out some holes. You want to segment, for example, a fossil, or trying to segment a cortex in the brain image like this. Pretty hard task, actually. Just want to check that the recording is running. Yes, it is. Some useful literature on this matter is John Ross' book. Again, it's a brick with many pages, and it covers a lot of material. So within that one, you can get a lot of basic information about thresholding and basic segmentation. The other part of the literature is about ROC curves. There is a presentation of a tool to produce these curves a little bit more in an automatic way. If you are doing a lot of testing, then it's easy improve your workflow if you can have an automated generation. So this is about that. So first of all, again, coming back to the basic question, why do we do the imaging experiments? So one is to explore some sample, visually investigate if you can't cut it, and sometimes you don't even have any prior knowledge about the sample. You can have some expectations, but not really detailed knowledge. For example, if you have archaeological artifacts, you never know what's inside, and sometimes it can be a surprise. Maybe if you shake it, you can hear that something is inside, but you don't know what it is. And the other one is going one step further to test our hypothesis. Then we need to do some kind of quantification out of the information you get from the images. So, like if you have an experiment with bubbles, is the temperature affecting the bubble size? Also, if the volume of canals in the bones, does it make them weaker or does it strengthen them, for example, and other examples. So, if we get an image, this is actually a cartoon, so it's not really acquired, but anyway, if you get an image of something like this, you want to investigate it and check what we have in it. And this is some kind of cell. And looking at what you get from the image modality, usually or often you get only a grayscale image. Sometimes you get vector images or multispectral images, but in the basic assumption, you get only a grayscale with some intensity related to how the sample responds with what you send through it. And then we make our imaging experiment, and in principle, we start out doing some projections in a tomography experiment that results in a sinogram, which is the information that you need to reconstruct a slice in 3D. And that is what you get here. And when you have done your tomography, you get a pretty big image. So in this case, we're talking about 2,500 squared times 2,100 times 32 bits, which results in 56 gigabytes of data per sample. That's a lot. Then from last week, the week before that, 2 weeks ago, I talked about image enhancement. Your image is noisy. You push that image through a lot of filters, whatever. 24 hours later, or 20 hours later, you still have 56 gigabytes of data, but it's less noisy, so it's easier to work with. So we need to do something now to reduce it, because handling this amount of data takes a lot of time, in particular if you're going to do segmentations, getting statistics out of it. And in principle, your goal is you want to have a plot with, say, 100 points in it. That's an extreme reduction of data coming from the 56 gigabytes, which is only one sample still. So if you want to see something progress, then you would have several times this. So what do we want? We can start from the practical point of view. You want to know volume fraction. You could ask for how many cells are present in the sample, how the cells are stretching, so it's a bit about the shape, and also how the cells are varying in volume, etc. So you want single numbers telling something about what you see in the image. And that is where the segmentation comes in, because you have to identify the regions that you want to measure on. And you can do it in different ways. Some you know about the approximate shape, so you know what you're looking for. You can easily put patterns on it, so that is a model-oriented way. And in principle, using Occam's razor, try always to do the most simple one, but not too simple. Then on top of that, we come to more complex things like using Bayesian statistics, neural networks that optimize algorithms to get more exact information. But why take the big machine of a neural network when a single threshold would be sufficient? That is the balance you have to make, not to put too much effort. You can do it because it's fun, but that's not the motivation, because you want your results in the end. And the next lectures I'm going to talk about techniques how to do this segmentation in more and more advanced ways. That's not last week, but anyway. What we did until now is that we looked at the images. They are noisy, and we have to apply some kind of filter in order to get rid of that noise. And typically, if we have a good filter, we have this noisy image, and in the end the output is you have 90% good information and 10% bad, or even better. Sometimes you can press the signal to noise ratio even better. If you have a bad filter, you enhance the noise, which is not what you want. So that is to be avoided. First thing when you get the images is to look at it qualitatively and what people are doing. So just looking at the images, saying something. Well, we can say we have small details here, we have larger here, we have so and so, approximately so and so many of this. But the idea is to just get an idea of what you're seeing. You can't quantify anything from those vague claims. So what you can do as a next step is to look at, for example, you can trace the outline manually, still relatively qualitative. You can also use the cut and weigh, so that means you're actually taking apart the sample and compare it to what the images give, so it's not really non-destructive anymore. But anyway, you can get an idea out of the images, and that principle you can also use in virtual, that you take fractions and analyze them in that sense. But we come back to this pie chart again, that there are different approaches on how to work with the data. Many of you are probably going more from the experimentalist. So you have your data and you have your questions, and probably also have some model, so you're going that way. Computer vision approach, then you would more think of it as signals and working on the data in that sense. And with a deep learning approach, you more go from you need to label the data somehow, so you need actually already to put some expert knowledge into the data, and then you tell this deep learning machine to learn what is expected out of that data. And from that, then you can make predictions on unknown data. So it's a little bit different approaches how you work with the data. And yeah, that was what I said just now. But anyway, going from the model, then you have your system, imaging system that produces an image for you. In the end, you have your imaging system, which includes the impulse, the sample, and how the system reacts with that. And then you have detection system that actually gives you the measured image. And the direct imaging approach is that you have different parts. You have the illumination field of the imaging system, and you have your sample, and those two are combined. So to get out the information you want, you have to divide the measured signal by the imaging system signal. And that is to get, in principle, I would say in many cases we're talking about transmission image. Or attenuation image, actually. The reason why I say attenuation image is that the beam is not always, well, no, it's a transmission image. Sorry, I'm messing it up this morning. The attenuation is something that happens to a certain part, but you have different reasons why the beam is not reaching the detector. So you only talk about the transmitted beam. For example, with neutrons, we have a huge amount of scattering, which is actually the main reason why the neutrons don't reach the detector. And they can be pretty annoying because they come back to the detector again, and not as structured as if they went through the sample. So let's look at a little example down here. We have a beam profile from some experiment system. We have the sample profile. That would be what you expect to see, but the detector gives you something else because it's the multiplication of these two. So you have darker regions out here. And looking at the profile, so this is a profile through the sample at some point, in the middle actually. Let's see. So it's somewhere around here that this profile line is made, and also on this one. And here you can see now that the orange curve here is the sample image. Then you have the green curve, which is the detector what the detector sees, and the blue curve is the beam profile. So you can see that there is sometimes a little bit amplification and sometimes attenuation of the beam compared to what you would expect to see. Down here there is a lot of attenuation because there is almost no beam. So this is actually a big problem when you start doing segmentation, Because as you could see on the previous one here, for example, this should be at this height, and then a simple threshold saying everything greater than this level would be okay, but thanks to the beam profile, it's far below this threshold and you wouldn't see it at all. So what we need to do is to look at this. So here we have it. So you can see here, these regions, they should be as bright as this one, but they are pretty dark, and if you put the threshold on this one, you will see these walls, but nothing else, and that would be wrong. In many imaging techniques, also absorption imaging techniques, you have X-rays, ultrasound, optical imaging, neutrons. They follow, in principle, Beer-Lambert's law, and that says you have an exponential decay of the intensity through the sample. So you have the input signal here, and then with the distance through the sample, you have attenuation. And that could be also based on position. So each position has a certain attenuation coefficient, and that depends on many things, depending on the modality. And but in principle, what we measure is this quantity here. If you do radiographs, this would be what you will see. If you do a tomography, you would see actually the X, Y, and Z information afterwards, and then in terms of attenuation coefficient. And seeing here on these curves, you can see that the detector sees one thing, and the true value is something else. And that also gives you a different spread in the histogram of the data. So the detector sees here, for example, this is pretty narrow. This is less narrow, and this is pretty wide. And if you see it from the attenuation coefficient side, they are more or less, not really, but more or less equally distributed in the materials. And that also is a problem when you start doing this imaging. Looking at this, you can probably tell that it's a kind of logarithmic scale in here. So by taking the logarithm, you would get pretty much better spread, and probably already look much more like this one. So a little example here. This is an example with a numerical model. Should simulate mammography. And here we again measure something based on a signal. We assume here now in this equation that it is homogeneous tissue, essentially. But it isn't really. So in the end, we come through to the point that it's actually a line integral through the material. So then we come to this equation, and the line integral goes over the attenuation coefficients at different positions through the sample. And we have two components in this image. We have air and we have breast tissue. And this has an attenuation coefficient all over, one pretty low actually. For X-rays, adipose tissue is pretty low attenuation, and from that we can start making our little model here. And you can see that we have air and we have the breast. So I can go on. So, and as we know that alpha is constant, we can actually detect the thickness of this breast at different positions, and then we would get an image. If you do a radiograph through it, you get an image looking like this, where black is 1, that means air, and this is the thickest part down here as the bright. The histogram of this looks like this. So we have relatively linear distribution of the gray levels, increasing here, and we have a large peak for the background. So already here, segmenting the breast from the background is relatively easy because you would set a threshold down here somewhere and you would have a pretty good separation already. And this would be the projection image instead. So now this image is the line integral through this volume data. And here we can see now what the thickness is. So now is the question, what happens if there is some kind of anomaly in the sample, so alpha is not constant, then it's impossible from the radiograph to tell if it's just thicker or if you had some other material. So if we have some kind of lump, like this, including it, and you can see that there is a great difference. And this, let's see here, so this looks like this in the radiograph, and it's pretty hard to tell from this one if it is a different thickness or if it is just something else. And in principle, what we would have is you would have the sum of alpha 1 through some thickness from alpha I di. So we would have two different thicknesses, and they would sum up into the signal. So that is the question now. Is this breast oddly shaped? All of a sudden there is some edgy cube in it, or is it actually a possibility that you have a tumor inside? That is the question now for the segmentation to make a conclusion about. So, I think I lost something here. No? Yeah. Okay. So, what can the segmentation give us? We can convert the images from something into something else. Mainly, we want to make a big reduction. So, going from, for example, 32 bits floating point data and squeeze it together into 1 or 2 bits, where we have, if you have 1 bit, then it's only true false, so it would be material, not material. If you would have 2 bits, then you could separate 4 different materials, and that already is a huge reduction in data amount, going from 56 gigabytes down to less than 2 gigabytes. And that makes it already more handleable in the memory. This one, you need a pretty powerful workstation to get the whole data into the computer, while this one could, with some desire, get into the normal memory of a laptop computer. And that makes it already easier for you to work with, play with it on under different circumstances. So the basic segmentation is we have the intensity image, which is actually a function in x and y, or z if you have 3-dimensional data. And we want to apply something, a threshold that distinguishes different regions in the image. Here I have a test image, only a background with a cross on it, and also added some noise. And this one can be segmented in some way. So looking first at the histogram, so the probability of different gray levels, then we have, in this image, we have a large mode here, which corresponds to the background, and then we have a smaller mode here, which corresponds to the item, the cross that we want to look at. So separating the two in the image means that you can put some kind of threshold here at this point, and you would make a pretty good separation between the two materials. And this is what we're doing. So this is setting a threshold that if it's greater or equal than 0.4, then we set it to 1. And if it's less, then we set it to 0. And applying this threshold, let's see if I can convince it to come up. No, I couldn't. No. Ah, there it is. Yeah. So now you can see that the threshold applied gives us a nice cross, but one here that was not so was misclassified was a confusing case for this simple threshold. And by testing different thresholds, we can see the effect of what happens when you apply them. So here I sweep over different thresholds. You can see here when you have threshold 0.1, there's a lot of background segmented as cross. Now when you increase it, that the background voxels or pixels, they get less frequent. And at the 0.42, then we have the ideal case, I would say, and then we continue increasing the threshold, and you can see that, oh, now we start losing the cross, and when you increase it even more, then we lose more and more from the cross, and in the end, it's barely recognizable. So this is when you just manually set the threshold, and that's also one part of the exploration when you explore your data, is actually that you just look at the histogram and play with the thresholds. Gives you an idea how easy it is to use a simple threshold, or if you need to use something more powerful. And that is something you can do, for example, in ImageJ, or you can also do it in Python. ImageJ is more interactive, so it's easier to play with. And if you want to segment cells, so that's a real sample. We can see that we have brighter regions and we have darker regions in this image. So in this case, you can see here they are. We have different sizes, and then you can also see that there is a slight gradient in this image, and that gradient is already a problem for us using a single threshold. So we need to get rid of that. And again, doing this parameter sweep using different thresholds, you can see that if you have a threshold at this point, there's a lot of missed objects, or they are too small. And then we increase it more and more, you can see towards here that you have a lot of background included also in the segmentation, which you also don't want to. So you have to balance it somehow. And in particular with the gradients, you have a problem with this normal simple threshold. So you need to do something to equilibrate the illumination in the image before you can do the segmentation. Then we have other types of images. Until now I've only been talking about scalar data, so one intensity value per position. But you can also have vector data, or so spectral data in each point. And for that, I have a little example here. Generate some a data table. We have X and Y positions. We have the detector intensity value, and we have a vector X and Y that describes some orientation in this data set. And looking at a histogram between the different features in this array, you have X and Y position. So X and Y, they are uniformly distributed across the data. If you see them together, you see a distribution like this. And then we have the intensity relative to position in X and Y. And here you have the histogram of the data. So it's a way to illustrate the whole feature. Along the diagonal, you have the positions, or you have the single information only, and then here you combine the two. And you can see that the vectors, for example, the x and y vectors, they produce a circle. And the intensity based on these vectors looks a bit strange, actually. And sometimes you can already tell from this way of visualizing the data, you can tell which features are more relevant than others to combine. And if you just would plot the x and y vectors, you would see a vector field like this. And what is also added here is the intensity of the detector is marked out as the color of this vector field. And applying a threshold to this kind of data, then you have to put some model knowledge into it. One would be just very simple. We say that if vector in direction x thresholded at 0.25 and also the one in y thresholded at 0.25, we would get something like this. So only a corner of the data would be extracted. And then you could play with that. But usually when you have a vector field, it's not really a single component that you want to threshold, but you want to combine them together. So you could, for example, say that you want to look at when x and y together provide some value. Let's see what's... that's just the histogram, and two-dimensional histogram of it. And you can already see that there is a circle like this, and in some cases you could say, okay, I want to combine them, that x, say, look at the amplitude of the vector instead of just a block in the corner. So we could say that if the absolute value of the vector is equal to 1, then I want to have this segment. And with that we can get a blob in the middle, for example. You can also look at orientations, so getting a certain pie slice out of the data. And yeah, you can be creative about how to extract this information. Most likely there is a physical interpretation that you want to put into this segmentation. And well, that was it for the first part. Where do I have my mouse? My mouse pointer is gone.